Hi, my name is Autumn McSwain, and this is my Lab 3 Black Holes report for Physics 2211 at Georgia Tech. So, to begin with, the purpose of this lab is to demonstrate the effects of Newton's second law and how it relates to momentum. Therefore, we analyze the motion of a star orbiting a black hole and to simulate the trajectory of a spaceship interacting with both a planet and its moons. So, this lab is structured in two different parts. The first part is to analyze the star's motion to find the net force on the star. We have to assume that force is only due to the black hole, and we use this to estimate the mass of the black hole. The second part of the lab is to simulate the motion of a spacecraft around a planet and a moon by calculating all the gravitational forces. We have to use the mass of the black hole from the first part to determine the initial velocity of the spaceship, and the goal is to make the spaceship orbit the planet and the moon while still being able to leave orbit. Some general overview of the findings was that the mass of the black hole was 1.519 times 10 to the 34th kilograms, and the initial velocity of the spaceship was negative 3.948 times 10 to the 9th, 2.97 times 10 to the 6th, and 0. So the procedure of this lab was to use the provided star code and glow to simulate the star's orbit around the black hole and generate positional data for the star's motion. Next, you have to analyze the star trajectory to calculate the net force on the star and estimate the mass of the black hole via Newton's second law. Using this, we could then use the second star code to simulate the spaceship's motion in comparison to the planet and moon using the mass of the black hole, and then we just adjust the spaceship's initial velocity to achieve an orbit that avoids crashing into the planets or the moon and is able to create a figure eight that leaves orbit. So some fundamental principles is Newton's second law, which is the acceleration of a moving object depends upon the masses of the forces acting upon it. This is shown by the equation F net equals delta P divided by delta T. From this formula, we're able to get the position of the formula, which is on the left, and the velocity of the formula, which is on the right. Another fundamental principle that is needed is the gravitational forces principle. The gravitational force of an object due to another object is an attractive force as defined as shown, where it can be rearranged by the mass of an object. So if gravity will equal g m1 of m2 divided by r squared will equal r hat, where g or gravity is defined as 6.67 times 10 to the negative 11th, and this can be rearranged to give us the mass of the second object will equal the absolute value of delta p over delta t, absolute value times absolute value of r squared divided by gm for the first object. The final fundamental principle that is important is parallel and perpendicular components of the net force. And net force can be described as having different components that are related to direction. So the combination of parallel and perpendicular components is what gives us F net as shown on the first equation. Parallel components are related to change speed of an object, and the position axis points in the direction of motion, or the positive axis points in the direction of motion. This is shown with the equation where p hat will equal p final minus p initial divided by t times p hat. Perpendicular components are related to change in directions of an object. This means that the positive axis points towards the center of the turning circle. With that, we will move on to part one, which is finding the mass of the black hole. So to begin with, you have to have a seed because this will be what creates the unique values that are needed, and my seed is shown above. Next, in the right box is the initial conditions, which are just most of the constants and the mass of the star that is given in the beginning as 2.0 times 10 to the 30. In the blue box underneath that is the calculating velocity for the star, which nothing really changes too much there. And then on the right is the important part, where it's mostly split up. The bottom part is most important, but from top to bottom, we have the initial and final velocities and their equations. We have p equals mv, define p initial and p final. We have the change in velocities and momentum via delta v and delta p. We were able to find dp over dt, where it equals delta ap divided by delta hat. We are also able to find f net in accordance to dp over dt, where f net will equal dp over dt. Next, we calculate the parallel of delta p, which is p hat equals norm, d mag pt will equal the equation, and so on and so forth. We are then able to find the parallel f net, which is dp dt pair, and then we're also able to calculate the perpendicular, where it's dp dt times dp dt pair. And then the very bottom is where we are determining the mass of the black hole by using the formula dp over dt absolute value times the absolute value of r squared divided by gravity times mass of the first object. And with that, it creates this elliptical shape. On the images, you can see that it is elliptical in the bottom shape, and in the top image, it shows you the parallel force and the perpendicular force, where the orange arrow is the perpendicular force and the blue arrow is the parallel force. So the F net was 9.052 times 10 to the 28th newtons. F net parallel was 3.954 times 10 to the 27th newtons. F net perpendicular was 9.046 times 10 to the 28th newtons, and this let us find the black hole mass to be 1.519 times 10 to the 34 kilograms. Now, with the mass of the black hole, we are able to move on to part two of the lab. So for part two, the beginning on the left, you have to have the mass from part one, which is shown by bh.m equals 1.519 times 10 to the 34th. Underneath that is the constants that are just needed, such as gravity, mass of the planet, mass of the spaceship, all of those things. Underneath that is the initial planet speed and velocity and the initial ship speed and velocity. Now, the initial planet speed and velocity was relatively normal. It was found using formulas and everything. However, the initial ship speed and velocity had to be calculated via trial and error, which is what makes this lab so unique. On the right is where a lot of the gravity forces are calculated. So first, FG on planet by black hole is calculated by the first chunk of coding. FG on planet by ship is then calculated, and via those two, we're able to find F net on the planet, which is shown in the blue box. Underneath that, we first have to find FG on ship by the black hole, and then FG on ship by the planet, which is able to then give us F net on ship. So we're able to find what the spaceship's gravitational net force was. And by creating an inertia position formula from velocity, we were able to find net force. By doing this, I was able to create this equation where you can see that the spaceship was the parallel, or the magenta line, where it's able to leave the circuit or the system like it was requested in the procedure. However, I was not able to get it to create an elliptical shape or a figure eight. And when I tried to make a figure eight, it kind of just like broke. So this was the best I could get as far as part two, where it would be able to leave the system. Now, y minus b. So there are possible errors, which boil down to basically just two, which are approximations and accuracy issues. So since this was done through a coded simulation, it will not properly represent reality. This will mean that some of the forces that could be acting on the system are not accounted for, which could possibly be making it so hard to create that figure eight that we were looking for. We also have to assume that there are no outside forces acting on the system, which may not be correct in reality. Furthermore, there are accuracy errors, as trial and error had to be used to find the spaceship velocity, and there may be a better velocity than what I was able to calculate. So that's also an error, as well as there could also just be like rounding errors from where I cut numbers too short or anything like that. Now, what does it mean? How is the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? So the net force is equal to the change of momentum and change in time. Net force is found by knowing each individual outside force exerting force on the system, and the rate of change of momentum is found by knowing the system change of velocity of motion. For this reason, they will differ because the net force is found from each individual outside force, whereas the rate of change is found by just knowing the system's change of velocity. Now, if you want to predict the motion of the entire system, what would you need to include in your computational model? Would there be any dominant interactions, or would they all contribute more or less equally? In order to predict the motion of the entire system, all the gravitational interactions must be included. This would cause the dominant gravitational forces to change depending on the relative position of the objects. This will make them all contribute unevenly as the system moves between what is in dominance between the planet, the star, the spaceship, the moon, and the black hole. It would all be changing and shifting because it is an ever-changing system, and that would make it really hard to compute in a computational model as the dominant forces would be changing. And that is my lab 3 report. Thank you.